Generally speaking, when objects are heated, I should say when they gain thermal energy, they expand. So generally, as temperature goes up, things expand. So length goes up, or area goes up, or volume goes up. So generally, as temperature increases, things get bigger. Water, under certain circumstances, is an exception to this rule, and that has some very important consequences that I'll talk about a little bit later. This expansion is proportional to the temperature change. And it's just, been studied and found that the length, how much a length changes, is proportional to a change in temperature. And it's also proportional to the initial length. So it is a fractional thing. And then there's this proportionality constant, alpha. So L naught is initial length. Alpha is called the coefficient of thermal expansion. Go figure. And page 545 in your book has a table that has alphas for a bunch of different things. And they also have values called beta, which I'll talk about a little bit later. By dimensional analysis, this change in temperature would have units of Kelvin, length would be meters, this length would be meters, so the meters cancel out, and we can see that our alpha has units of inverse kelvins, 1 over Kelvin. So it's a per Kelvin sort of thing, per temperature change, which makes sense. So if we're given this data, we can calculate the temperature change required to produce a given thermal expansion, or how much something expands, or what the alpha is. An interesting application of that is something called a bimetallic strip. There's a strip of metal, two metals, bimetallic, two metals that are kind of pressed up against each other like so. So this is metal 1, this is metal 2. And they have different coefficients of thermal expansion. So as it heats, let's say that 1 has a greater alpha than 2. So as it heats, 1 gets longer. Say alpha 1 is greater than alpha 2. So as temperature goes up, 1 gets longer, but they're scrunched together, which means that they wind up curving because they're stuck together, glued together somehow, so they can't separate. So instead of just stretching out, it gets longer, but then it also kind of yanks 2 along with it. Likewise, as temperature goes down, then it would bend the other way because 1 would contract more than 2 also, and so then it would curve upward. Bimetallic strips are used in a couple of different applications. You can create a thermometer out of this, although generally they just use something like mercury that has a known coefficient of thermal expansion, and so you can figure out what the temperature is based on how much the substance expands. A more common usage of this is a fridge, so that there's this strip that acts as a switch in the circuit, whatever the heating circuit is. So there's this switch, and so that as it expands, as it gets hotter, for example, it curves to close the circuit, and then as it gets colder, it curves to open the circuit, and when the circuit is closed, the fridge is working and cooling stuff, and then once it reaches the appropriate temperature, then the strip will bend and open the circuit again to turn the fridge off. There's a similar thing that some faucets have a safety thing so that the flow of water will be blocked if the water gets too hot. That it functions off of a bimetallic strip. Another way that thermal expansion is taken into account, this is not a bimetallic strip, but on bridges and stuff that are made of metal, long objects that are made of metal, they had expansion joints so that the metal can expand and contract without, doing any damage to the concrete or cement that's in the bridge. So bridges have these, railroad tracks have these, also oil pipelines. Bridges, railroads, and pipelines. And basically what that looks like is that instead of, when you have your two pieces of metal, instead of just laying them end to end like this, because if they expand or contract, damage could happen, they'll have them kind of, they'll have it hooked in, but then there's some kind of like connector piece here, and they're locked together by using this connector piece, but there's extra space in here for them to be free to expand without putting strain on the bridge or the railroad or whatever. So just likewise, just as length expands, that would be talking about like a metal rod or something. Area, similarly, also expands. And area, this is like if we have a sheet of metal, talking about how much that would expand or contract. Well, area is always proportional to length squared. So a new area would be equal to a length plus a change in length squared. And we know our change in length from our equation on my previous page here. I said that a change in length is equal to alpha L naught delta T squared, and if we FOIL that out, we get an L squared, we get an alpha L naught delta T, and then, 2 alpha L naught delta T plus an alpha squared L naught squared delta T squared. Now, alpha delta T is typically less than 1. Therefore, the alpha delta T squared we can say is negligible and just ignore that last term, which gives us that our our new area is this, or is proportional to this. Our new area is going to be our new length squared, and so therefore this is our new area. This is our original area. So if we move that over, that becomes a change in area, and that is equal to our 2 alpha. This L was the original area, so that should be an L naught as well, just as this was an L naught. So that's 2 factors of L naught. That's 2 alpha L naught squared delta T, and an L naught squared is just our original area. So that is a result that we can use when dealing with area expansion. And following a similar argument, a volume winds up being a 3 alpha V naught delta T, because if we cube a binomial, we get coefficient of 3 stuck in there. And this, for volume, for whatever reason, they use a slightly different variable. They use B, or beta, which is the coefficient of volume expansion. And we can see that beta equals 3 alpha. So if we're doing a volume expansion with a metal of some kind, the alpha is given, so it's better to use 3 alpha. For liquids, generally beta is given because we don't really care about length expansion for liquids, and that's why those are given in terms of beta, or gases. Those are given in terms of beta rather than alpha. interesting application of this is that sometimes a container will expand more or less than the expand or contract more or less than the liquid inside it, which is actually why in a gas tank in the car there's an automatic shutoff before the tank is all the way full, because the gasoline will expand more than the container that holds the gasoline, and therefore it would spill if it was full all the way to the top.